focus on problems of constructing and the existence of Lagrangian fibrations, leaving the description of their structure to other speakers. Kenjo Giza will speak later about degenerate fibers of Lagrangian fibrations. So, a Lagrangian fibration is a proper morphism from M to B with connected fibers such that M is symplectic, well, surjective proper morphism. And the generic fiber of F is Lagrangian. So, and here dimension of B is half the dimension of M. So, there are different kinds of problems with Lagrangian fibrations. So the principal algebra geometric motivation is the study of reducible symplectic varieties. So what is known about Lagrangian fibrations on irreducible symplectic varieties? I fix notation V and irreducible, well, I'll say Keller. Sometimes it will be projective. A Keller reducible symplectic variety with its Moville, Bogomolov, Fujiki form, Q. It's an integer form, quadratic form on the lattice H2. Okay, so so there are two. Well, this is two versions of the same conjecture for these manifolds. So V is B meromorphic. To a reducible symplectic variety V prime with a Lagrangian fibration, if and only if there exists C in Picard of V with Q of V 0. Q of C. Q of C. And the conjecture suggests that the Moville-Bogomolov form behaves like intersection form on K3 surfaces. In this way, one can characterize K3 surfaces with elliptic pencil among all the K3 surfaces. And a more precise version of this conjecture, let V be a projective, reducible symplectic variety, L non-trivial line bundle, then L is nef with Q of L0, if and only if the linear system L defines a Lagrangian fibration with base Pn. Okay.
Why is project? Why do you want it to be projective here? Are there counterexamples for?
No. So you suggest I put Keller here.
Yeah.
Okay. Okay. Anyhow, one can be more or less careful about the conclusion. One can say that some multiple of L gives a Lagrangian fibration, or one can replace the base by something more general. Anyhow, there are no examples with base different from Pn.
Of course, NEF for things which are not projective maybe not stronger. I mean, NEF sort of assumes there's not curves to check the.
There is a notion of net.
Yeah.
Yeah, in the closure of the Keller call. Yeah. Now I'll first say a few words about partial results for general. Reducible symplectic varieties, and then speak about particular families of irreducible symplectic varieties. So the most important result here is Markushevich theorem, which says that whenever we have so if V is an irreducible symplectic variety, F any fibration morphism, a morphism with the dimension B strictly, well, surjective morphism. With dimension B strictly between 0 and dimension of V, then F is a Lagrangian fibration. So that dimension of B should be half dimension of V. Do you hear me as good as without? It's a recording.
It's not for us.
Ah, okay. Okay, so there is another important result by Junmuk Wang, which says that whenever we have a Lagrangian fibration with V B smooth. Okay, V is by definition smooth, but we claim that B is smooth. Then B is Pn. So this lets us hope that the conjecture with Pn here is a right version. And the third result is deformation invariance of Lagrangian fibrations. It uses Matsushita's theorem on higher direct images. It says that if we have a Lagrangian fibration with well, projective V and B projective and smooth, And then high direct images of OX omega I of B. So this implies for any so if B is Pn, if we know that the B is Pn, we know this by result of Wang. So if B is Pn, L the lift of O of 1, then H0 of L is n plus 1, Hi of L as 0 for I strictly positive, and this implies in its turn by the semi-continuity argument that for any deformation, so I write curly letters for families over, well, of VL over some irreducible base delta in the class of Keller irreducible symplectic varieties. The linear system of the deformed L, I noted LT, defines a Lagrangian fibration for T in a dense open, well, in an open subset, in a Zariski open subset. Of delta. So the Euler number is preserved. Hi cannot jump in an open neighborhood. So, and the base point freeness is an open condition. So. Okay, so reformulation in terms of modular spaces. So if we fix a Keller reducible symplectic variety, lambda it's Bouville-Bogomolov lattice, so a marking of an irreducible symplectic variety V deformation equivalent to V0 is an isomorphism of its Bouville-Bogomolov lattice with lambda. So we define period domain in a standard manner. Well, I denote by Q tilde the bilinear form polar to quadratic form Q. And we have the period, so M, we introduce M modular space of marked irreducible symplectic varieties deformation equivalent to V0, and we have the period map. So it's well, it's smooth. It's known that it's smooth, but non-separated. So it's not a manifold in the standard mini. And there is period map, which sends a marked irreducible symplectic variety to the line, well, H20. So it's a line in this vector space, and it's a point in the projective space, and in fact it's in omega. And so now to any class, non-zero class, in lambda we can associate a smooth hypersurface HC in omega, which is just the inverse image of the hyperplane of classes orthogonal to C.
You wrote omega, you meant M.
Smooth hypersurface in M.
In M, yeah. Yeah. Okay, so the proposition which reformulates this last assertion is assume that V0 admits a Lagrangian fibration given by linear system of some line bundle. Then F deforms to Lagrangian fibrations phi LT from Vt to Pn for T a Lagrangian fibration, well, with the same hypothesis that B is Pn. Lagrangian fibration over Pn. So this means essentially we assume that B is smooth. For T running over some Zariski open neighborhood of the class V0 in HL. Okay, so in the direction of this, one can ask what happens without this assumption that we have already a Lagrangian fibration at some point of this hypersurface. So there are general result of Verbitsky. So 2009. So assume C is a class, non-zero class with zero Bogomolov square. Then for any, well, then for very general V in this hypersurface HC, V contains non-trivial co-isotropic subvarieties Z of codimension P, which is smaller than n half dimension of V. So this includes in particular the case. Co-isotropic means that the rank of the symplectic form restricted to this variety is as small as possible, but it takes minimal value. So in particular, when P is n, we get a Lagrangian submanifold. So this statement includes the case of Lagrangian fibration, but it says that if there is no Lagrangian fibration, then there are co-isotropic submanifolds. So it's some advancement towards the wanted statement. And there is also a result of Campana, Oghiso, Peternelli in the same direction. Which was, so I don't know which year, but it was before. It says that under the same assumptions, V contains non-trivial subvarieties of dimension greater or equal than 2, I think, or greater than 2, I don't remember. Okay, so if
isotropic or what kind of varieties?
I don't remember. Not.
What we show is that algebraic reduction maps.
Yeah.
And we do not claim anything about the resistance.
So,
of varieties.
so you do not prove what I write. Okay. So and then okay.
Because there's no.
But I think in dimension 4.
It's not like that. It's not.
Maybe what I wrote was right in dimension 4.
Yeah, I think they proved that in
What we
dimension 4.
proved is that in dimension 4, algebraic dimension is 0 or 2 or 4.
Yeah.
But we did not exclude the case of algebraic dimension 0.
Ah, okay. Okay. So okay.
That is a kind of abundance.
Mm-hmm. Okay.
Non-vanishing, we do not.
Okay. So well, one can correct what I wrote by adding the hypothesis that algebraic dimension is not 0. Okay. But okay, then it's trivial. Okay. Yeah. Okay. So now I'm passing to particular classes of reducible symplectic varieties. So first, Gilberts powers of K3 surfaces. So we take V Hilbert power of a K3 surface S, and greater or equal than 2 lambda. Its Boville-Bogomolov lattice is a direct orthogonal sum of the lattice of K3 with one-dimensional lattice given by E squared is 2 minus 2n. And so Q represents 0 in Picard V if and only if there is an H in Picard S such that H squared is M squared 2n minus 2 for some M non-negative integer. Then the elements with square 0 with respect to Boville-Bogomolov form are H plus minus ME. And there is a theorem. So it was proved by Hassett and Chinkel for N2, well, somewhere 99. Then by myself in 2005 and by Saban 2005. Let S be a K3 with Picard group Z, and this relation satisfied. Then there exists a flop such that the image of H minus ME defines a Lagrangian fibration on V. And I will add several remarks. So mu is a trivial an isomorphism for M different from 1. So the proof is Yoshioka's and it's included in the paper of Saban. And one more remark. If we take all these classes, primitive with square and MZ, so probably I should write M before because H depends on M, form a single orbit and monodrop group. So this means if we want to use this statement for the result of the kind of the proposition which I stated before, then we really do not need all these different cases. We have to treat the case of m equals 0 only, and all the other will be obtained by the action of the monodromy group. And in the case of m equals 0, the result is trivial because if the K3 surface has an element h with square 0, then it has an elliptic pencil, and we can just take symmetric power of this elliptic pencil to get a Lagrangian fibration on this guy.
The assumption is because
Then S is not projective.
What?
Then S is not projective under the assumption.
So here it's projective. Here it's projective, but when we take the deformations to the hypersurface and the modular space, we speak about very general element of these hypersurfaces. So we can use only this result for m equal to 0 to get the result for all the hypersurfaces of this type.
If m is equal to 0, it's probably not projective, because it's one-dimensional Picard and h square is 0, right?
Okay.
But it doesn't matter.
Okay. Okay. So for m equal to 0, we can have even more general result that I wrote. Yeah.
Do you know anything about the base of Lagrangian formation?
The base is always Pn.
It's Hilbert scheme of CP1.
Well, for m equals 0, yes, but for other m...
It's always Pn. It's always Pn. Yeah. Okay. The construction uses twisted modular sheaves. So I'll tell it only for m greater or equal than 2. And we take the following for a Mukai partner of our original K3 surface S. So this is a modular space given by Mukai vector, which is isotropic. This means that it's a K3 surface. It's non-singular, so it's non-singular because the vector is primitive. But it's not a fine modular space. It has a Poincaré, so universal twisted sheaf P. So it's twisted by, so it's on S times Y, twisted by the lift of its I prefer to write alpha to minus 1 here than in the sequel. For some alpha in the Brouwer group of Y. And we have the twisted Fourier Mukai transform given by its dual from the derived category of sheaves on S to derived category of twisted sheaves on Y. And its inverse, which is given by the dual by P. And when we apply it to our Sn, which is modular space of sheaves with the Mukai vector 1. So these are ideal sheaves of n points. I put the rank here, and C1 is 0, and this is chi of the sheaf minus its rank. So it's 1 minus n. So when we apply the Fourier Mukai transform, we obtain a twisted sheaf on B. That's an element of modular space, which I denote like this. It depends on some additional choice, a B field which lifts the element of the Brouwer group. I will not be very precise about this. The lift is not unique, and the third component of the Mukai vector depends on this choice, so if it does not have any geometric sense, I do not write it here. So L is, so we get rank 0 sheaves, so they are supported on curves. Curves are from the linear system L, which is primitive, and in fact the Picard of Y is also Z, so this is a smooth modular space by Yoshioka. And it has a Lagrangian fibration, which is support map. Each sheaf is sent to its support. So it's a Lagrangian fibration map. So this is how it's constructed. So a priori, this is a rational map. Well, in fact, we have to apply also the first cohomology here, because the image is a complex which concentrated in the first degree. So there is an argument of Yoshioka which shows that in fact it's a regular map. Okay. Now there are similar results for generalized Kummer, which are in fact not so strong. So for generalized Kummer, so only case m equal to 1 is treated. This is paper by Gilberts. And so what's left? So the case m greater than 1 for generalized Kummer. So m, in both cases, m is the coefficient of the exceptional divisor E. And case when H is not primitive. So in this statement, Picard is generated by H, but we can also have so this for both series Sn and Kn, but we can also take H equal to Kl with relation Km relatively prime. And so look at the linear system Kl minus Me. It's not clear whether we can construct a flop here to a non-singularly irreducible symplectic variety with a Lagrangian fibration. So it's not known. So question does linear system of L define a Lagrangian fibration after a flop? So there are also similar questions which one can ask about other known families of reducible symplectic varieties or gradients of dimension 6 and 10. So already he worked in his paper about his example of dimension 10. He considers a K3 surface of degree 2, and then his variety is birational to a Lagrangian fibration. Okay, but this kind of questions, what happens to how many hypersurfaces, how many orbits of square zero are there, and can one get Lagrangian fibrations for generic members of all of these orbits? It's unknown. This is unknown. Okay, and of course, there are many questions for non-specific families. For example, one does not know the properties or the general properties of the Bogomolov form Q. One does not know whether it's even. It's even in all the examples. One doesn't know whether it's indefinite. So if there is an reducible symplectic variety with a definite Bogomolov form, then there are no classes with square zero. There are no Lagrangian fibrations. And we don't know whether such examples exist.
We don't believe that.
We don't believe that. Yeah.
I mean, like three-dimensional would be 2, would be 2 equal to 3 or something.
What?
I mean, the signature that was 3 plus the rest, right?
Yeah, it could be 3. So
But could be 3.
It's a first assumption, you know, so.
Okay. All right.
Okay, now I want to say a few words about prime Lagrangian fibrations. So I'll start by the remark, all known Lagrangian fibrations on reducible symplectic varieties have general fiber with polarization of type either principal or (1,1,1,1) K, where K is greater or equal than 3. So the natural question arises whether one can hope to get other types of polarization. And in fact, in this case, all the known examples are Jacobians of curves. Question are the reducible symplectic varieties with other polarizations. I will speak about an approach to this question. Prime fibrations from K3 surfaces with anti-symplectic involution. So we start with the K3 surface acted on by an involution I. The fact that it's anti-symplectic, this means that if we take sigma s, the generator of the canonical bundle, then I up star sigma s is minus sigma s. And now, if we take some linear system of curves, of genus G on S, assume its class is invariant under the involution. Well, then this linear system is a projective space PG, and it has two fixed complementary projective subspaces fixed by iota. So they are not, their roles are not completely symmetric because one of them contains. Their roles are completely symmetric if iota is base point free. So if the quotient is in request surface. If not, there is a branch curve, and for one of these projective spaces, all the curves contain branch curve as component. So it's a bad subsystem. We take the good one, where generic member is a irreducible curve. And so we have so I represent this linear system as family of curves over PG. We restrict it to PG1, so to the good component of the fixed locus. Then we have, on this family of curves, we have a fiberwise involution iota. And we obtain the Lagrangian fibration P, which is the compactified prime variety of this, relative prime variety of this family of curves. So it's fibered over PG1 with fiber prime variety. There is no general theory of compactified relative prime varieties, but here we can work inside some modular space of sheaves on the K3 surface. We can define this compactified prime as the following thing. Take the modular space of torsion sheaves. This is a compactified Jacobian. I cannot take a generic polarization here because I need that polarization be invariant under iota. And it turns out that this modular space is singular because polarization is not generic. So we take the fixed locus under the composition of two involutions, two commuting involutions. This is again involution. -1 is a standard inversion on the Jacobian. iota star is just pull back with respect to our involution. Take the fixed points. So it's something smooth and symplectic out of the single locus of the original ambient variety. But it has many components, so we choose one component which contains the zero section of Jacobian varieties. So this is the definition of the compactified prime in this case. Only one example of this kind has been computed up to the end. This is our paper with Tikhomirov, 2007. Take as generic quartic with involution, which is given by just changing the sign of one of the coordinates in the projective space. So a kind of symmetry with respect to a plane. And in this example, P has it's a singular reducible symplectic variety. P has 28 singular points of type C4 over -1. So these are not resolvable in a symplectic way, but these are symplectic singularities nonetheless. In fact, Fujiki, many years ago, around 30 years ago, presented a list of examples of reducible symplectic varieties with sufficiently nice singularities. And there are two examples in his list with 28 singular points like this, with the same Euler number between them, but our Euler number is different from Fujiki's, so our example is new. Okay, so which questions can we ask in relation with this construction? Study other pairs. Si. Then determine the Bogomolov lattice. We should add Namikawa here because it's Namikawa who studied Bogomolov form for singular varieties. But well, it's unknown. One should compute it somehow for these particular varieties. One can consider more generally varieties of the form. Take some modular space acted on by a symplectic automorphism group. J finite symplectic. Take some component of it. It's a generalization of this example because each of the two involutions here is anti-symplectic. Their composition is symplectic. So we take the fixed locus of symplectic involution. We can replace involution by any finite group, and we'll get also symplectic components of this locus. Well, and one can also suggest that there are no Yeah, I forgot to say here that polarization is so Lagrangian fibration. Fibers of P P2 have polarization one, two. So the conjecture is that there are no other irreducible symplectic varieties with mild singularities with a Lagrangian fibration of type 1, 2. So this is for dimension 4. Mild means symplectic of codimension strictly greater than 2. Symplectic. Of course, one should make it more precise. Okay, but so there is Barth's theorem, which says essentially that all the 1-2 polarized varieties are primes of such double covers. So this question about families of prime varieties somehow. Okay, so what else? One can get some constructions of Lagrangian fibrations over non-compact basis. From Hodge theory. So these are Lagrange fibrations of intermediate Jacobians of some varieties. So, for example, the following construction. Take for B the base, the moduli stack of Fano three folds V containing a given K3 surface S as anticanonical divisor modulo isomorphisms fixing pointwise S. So that's a smooth stack. The Lille-Mumford stack, which was introduced by Beauville in 2002, and its tangent space is H1 in tangent fields, tangent vector fields vanishing on S, which by Serre duality is the dual of H2 omega 1. This is the tangent space cotangent space to the intermediate Jacobian of V. So we have a natural way to identify the tangent space to the base, to the cotangent space, with the cotangent space to the fiber. This is the situation of Lagrangian fibrations, and indeed, the relative intermediate Jacobian can be represented as a quotient of the cotangent bundle of the base by some local system of lattices. And to prove that this is Lagrangian fibrations, one should show that the sections of the local system are Lagrangian. So this can be done by Hodge theory. So F is a Lagrangian fibration. So this gives around 50 Lagrangian fibrations over some non-complete bases, which are these stacks. Well, there are natural questions around these. Questions try to compactify. And of course, look at the basis and a few examples which I explicitly looked at. These are always open sets of projective space. If we take some particular families, then particular members can have automorphisms. Then this should be considered as a stacky projective space. Well, and so in this case, we have the family of intermediate Jacobians is identified with the relative Jacobian of curves on a K3 surface, which is Fourier-Mukai partner of this. So this is in fact the easiest case of the previous theorem about twisted Fourier-Mukai transform. Here, in this case, we have a compactification of the family of intermediate Jacobians. And there is another case, 10-dimensional example, which was studied by Huang and Nagai. This is the case when S is intersection of a quadric and a cubic in P4, and V are cubics containing this. So here the base is 5-dimensional, so the total space of the relative intermediate Jacobian is 10-dimensional. And Huang and Nagai study Lagrangian fibration on the modular space MS 2, 0, minus 2. This is singular modular space because the Mukai vector is not primitive, and it has a resolution of singularities of O'Grady. Huang and Nagai identify some open subset of O'Grady's resolution of this modular space with some torsor under relative intermediate Jacobian of the integral system of this type. This gives a partial compactification of this torsor. I will stop here.